Okay. So today's topic is reliability evaluation of protection systems. Okay. So far what we have discussed: plant and station availability, okay. There we considered boilers plus generating sets. Then we considered auxiliary systems, and because of the auxiliary systems, how derated states are possible, though not completely out of service or zero output. And so this was lesson 25, 26. In lesson 27 we discussed this. Lesson 28 we discussed allocation and effect of spares, right? Okay. So the last part of this whole plant and station availability is the reliability evaluation of protection systems. Now to understand this reliability evaluation of protection systems, we need to know two concepts. Okay. So one is known as event tree, the other one is known as fault tree. Okay. We'll start with the event tree. So what is event tree? An event tree is a pictorial representation of all the events which can occur in a system. It's a pictorial representation of all the events. We'll shortly see how an event tree looks like for a protection system. Okay. It is defined as a tree because the pictorial representation gradually fans out like branches of the tree. So as we will see, one event, what other possible events, what other possible events. So just like branches of the tree, it fans out. Okay, this is called fanning out. Okay, therefore it is defined as a tree. So where we can use this method? For systems in which all components are continuously operating, or for systems for which some of the components are in standby mode. Okay. Both are applicable for electrical systems. In practice, the event tree method is most widely used for safety oriented systems, just like protection systems, safety oriented systems. For the above two systems, the differences can be as follows. That means the one which is continuously operating and the other is the safety systems. With continuously operated systems, the event that can occur can be considered in any arbitrary order, whereas for standby systems, sequence of events must be considered. Okay, for protection systems, sequence of events must be considered. The starting point for a continuously operated system is generally the normal state, whereas for safety system, one initiating event is considered which can be random, which can be anywhere in the system. Okay. So that is known as, so these are called event trees, right? Then the next one is fault trees. Okay. So I'll ask some questions. So for protection system, what methods you are going to use? Anyone who can tell? Somyashri? Vishwajit? Priyavrata? Anyone can tell?
Yes, sir.
For protection systems, what methods you are using?
For protection system.
Hmm. What we discussed, what methods we are using? We are using two methods. Okay. One is the fault tree, the other one is the event tree.
Yes, yes. Yes, yes,
Okay.
yes, yes.
Okay. So what is an event tree? So I have shown you it is a structure like this. This is the event tree. Okay. Whereas a fault tree is some kind of a top down approach or down to up approach where we segregate various components into small components, okay, in a bottom to top manner. Okay. One method of evaluating failure probability of a subsystem. So here we say it is a subsystem. Okay. So it's a subsystem. One method of evaluating the failure probability of a subsystem is using fault trees, though not frequently used for topological type. That means network systems. Fault tree uses the logic that is essentially the reverse that is used in the event trees. Okay. So both are similar things, but fault tree uses a different logic. Okay. In this method, a particular failure condition known as the top event. So we have got some event known as the top event, okay, which is considered, and a tree is constructed that identifies the various combinations and sequences of other failures that lead to the failure. Okay, so what are the various combinations or sequences that lead to the failure? The process starts by first identifying a specific mode of failure to be accessed. Okay, what failure we are considering? The causes of this failure are gradually broken into an increasing number of hierarchical levels until a level is reached at which the effects of the failure of the basic system components can be identified. Okay, so here the important is basic system components. So we go on segregating the system until we reach the most basic level or elementary level. The method is frequently used as a qualitative evaluation method in order to assist the designer, planner, or operator deciding how a system or subsystem may fail as a result of individual component behavior and what remedies. So how we can alleviate such a scenario. Okay. So now let's see how a fault tree looks like. Is the blank screen visible to everyone?
Yes, sir.
Yes, sir.
Okay. So be attentive. This is very important concept from the exam point of view as well as your requirement also. So how does a fault tree looks like? Okay. Now suppose we have this system. So this is the main grid. The main grid. So from the grid, so there is a substation or a transformer. Okay. Now this can be a typical EV charging station also. Okay. So you have got two converters connected like this. So this is, so these are the, one second. Okay. So this can be a typical EV charging station or special purpose machine. Okay, so here it is, we'll say this is converter A, and this is converter B, and this is the substation, and this is the grid. Okay, and this can be a special purpose machine or EV charging. Okay, anything. Okay, so anyone who can tell me why I have drawn this diagram, what you are going to see?
To show the network like suppose
Okay, so we are going to develop fault tree for this particular system, which may resemble a EV charging station. Okay, so what we discussed, that this can be a typical EV charging station. So suppose on the top of the hierarchy there is this EV charging, for which we are going for a DC supply. Suppose because of some fault there is no DC supply, so that is what we see eventually. Okay, no DC supply, that means our charging is not happening. So what can be the reason for that? So for that you can have, so you are going to see whether the fuses are blown or not, etc. So there can be two events. So one like this. Okay, so this is, I would say, no power supply to converters. Okay, or the converters fail. Converters fail. Okay, that means there is power supply, but somehow the converters fail. Now why there can be no power supply to the converters? What can be the reason? So we can have the following reasons. Okay, so one, I would say F1 failure 1, which is grid failure. So there is a complete grid failure because of something. So there is no power in the grid itself. Or the transformer failure. Okay, you can say that to be substation failure. Okay, now why the converters will fail? So you can have an AND situation here. So both converters will fail. Converter 1 fails and converter 2 fails, because one converter may be able to supply some of the power demands at a reduced capacity. So only when the both converters fail. Okay, so this is a typical, also I would say this is F3, this is F4. So this is a typical fault tree for the system that we have shown here. Okay, right, so this is a fault tree. Now event tree in detail we are going to see further. So since we are just discussing the concepts behind protection system, so this is what we will discuss about fault tree only. Now we will discuss in detail about the event tree for a protection system. Okay, okay, so we were here, we were discussing fault trees, and we discussed in detail how to construct a fault tree. Okay, now you see the various concepts related to the, now that you are aware that what techniques to use for evaluating the protection system reliability, we will discuss the various concepts. The value of the stuck breaker, that means you have given a signal to the circuit breaker but it is not operating. So what is the probability of that? So that can be established from a data collection scheme by recording the number of requests for a breaker to open and the number of times the breaker failed to respond. The probability of a breaker corresponding to a failed component depends on the protection system, its construction, and the quality of components being used. Okay, so this is a completely integrated system of its own, and as such can be analyzed independently of the power system network which it is intended to protect. So that means protection systems or the circuit breakers we can consider to be a independent event with respect to the power system. So how a protection system can malfunctions? One, it fails to operate when required. That means there is a fault, the protection system should operate but it doesn't operate. The other one is there is no fault, it operates. That is called spurious or inadvertent operation. Okay. So how to model the system? So first, the basic structure of a protection system. So there is a fault detector which detects the faults maybe through CT, PT, etc. Then there is a relay which gives a trip signal to the breaker B. Note the terms FD, fault detector, relay, trip signal, and breaker. Protection systems involve sequential operation of a set of components and devices. There are several alternative techniques available including fault trees, event trees, and Markov modeling. We have seen the event tree technique is particularly useful because it recognizes the event tree technique is useful because it recognizes the sequential operational logic of a system and can be easily extended to include analysis of the system at increasing depth. So how to evaluate the reliability of a protection system using fault event trees? Consider a particular network component that is protected by two breakers B1 and B2. So we have got two breakers. Assume that both breakers are operated by a same fault detector, relay R and trip signal TS. The event tree shows the sequence of events together with the outcome of each event path. So now I would suggest you write down this. Okay. So what exactly the event tree shows? The event tree shows the sequence of events together with the outcome of each event path, only one of which leads to complete success when both the breakers open as requested. So the point to note is only one of which leads to complete success. So there are several paths, but there is only one which leads to complete success. The event probabilities needed are the probability that each device will and will not operate when required. The time at which a device is required to operate is a random variable. Okay, it's a probabilistic random variable. Okay. The only single index that can be calculated to represent the probability of failing to respond is the average unavailability of the devices between consecutive tests. So this slide is about how to obtain the data. So this is the event tree. Look at it. So this is the event tree for our protection systems. Okay, look at it. So I told there is only one path, which is the success path. You see, a fault occurs. Here it operates, then operates, and finally where both breaker B1, B2 opens. So this is the case where a success case is there, both the breakers open. Then there are many cases through many paths with which the protection system will fail to operate. Okay, so these probabilities we have to obtain. Okay. So what mathematical techniques we are going to use? Assume that the time to failure of each device are exponentially distributed. The time period between the consecutive events is say Tc. That means you have given a trip signal, the breaker either opening or failing. The average unavailability of the device is given by this equation, 1 by Tc, 0 to Tc, the exponential distribution. This is actually exponential distribution. Okay. Then if lambda Tc is much less than 1, the unavailability of the breaker is simply given by the failure rate of the breaker to operate into lambda Tc by 2. So this is the formula that you are going to use in this case. U is equal to lambda Tc by 2. Now how to evaluate the outcome probability. That means there was only one outcome where all the breakers opened, whereas there are many cases the breakers did not open. Okay. The evaluation of outcome probabilities is a simple exercise after the event tree is reduced. First, the paths leading to the required outcome are identified. The probability of occurrence of each relevant path is the product of event probabilities. So we just simply make the product of the event probabilities. The probability of occurrence of the outcomes is then the sum of the probability of each path. Okay. For example, in the present example, probability of B1 not operating, probability of path 3 to 7. You see here. Okay. So if you see here, B1 not operating. So B1 operates only in these two cases. So from this onward, that means point 3 to 7. So B1 is not operating. So you have to multiply this, then add up this. Okay, that is what it is saying. Then B2 not operating, 2, 4 to 7, 2 and 4 to 7, not 3. And both B1, B2 are not operating, paths 4 to 7, you can see from there. Okay. So these are some of the examples I have taken from the book for the values. Okay, what is the probability of various paths which is not operating? Okay. So failure probability, which are very less, of course, you can say. So that means you see the success probability is about 90%. So you see this. So the path 1, which is a success case, both breakers open, is about 98% over 3 months, 97% over 6 months, and 95% over 1 year. Okay. So what happens when there is sharing of the protection components like main and backup protection, etc.? It was assumed that the breakers B1, B2 were both actuated by the same fault detector, relay and trip signal device. Consequently, both breakers shared the same protection system and failure in the system. So that what we consider. Other than the breaker itself caused both breakers to malfunction. Okay, this possibility is reduced by providing alternative channels like backup protection. Assume that the two trip signals are used. Okay, one that actuates breaker B1 while TS2 actuates breaker B2. This is another way. Although the struck probability of B1 only and B2 only remains unchanged, that of B1, B2 together is considered as reduced if you have two different actuator signals. Okay. So this is the event tree for that, where we have got two different trip signals, as you see here. So we have got two different trip signals for each of the breakers, and we construct the event tree. What we have to obtain from the event tree? We have to obtain from the probability of each of these paths. Okay, each of the paths by multiplying the probability of each of the events along the path, then adding up this 1, 2, 3, 4, 5, 6, 7 depending on our requirement. Okay, fine. So with this we conclude the concepts of reliability evaluation for protection systems.